Hey, Honors Chem, this is Mr. Lambert once again. We are going to quickly cover section 8.2 in the text, Balancing Chemical Equations. We have been introduced to balancing equations in some of the lab experiments that we conducted while we were still in the classroom. There were certain equations that I wanted to balance, even though we hadn't covered this particular section yet. So this will look familiar to most of you, but as a class, we need a quick little lesson on how to write these things called coefficients, these whole numbers in front of a chemical equation, so that it is balanced and it obeys the law of conservation of matter. Okay, the first example problem, as my board is falling, the first example problem is example problem 8.2 on page 228. Notice I have the pages here in the section that I'm covering. There's the title of the lesson. What we have is an unbalanced equation from words. What I did not write out because I didn't want it to be too messy is that the problem actually gives you the chemicals. It tells you what's happening, and we had to write a chemical equation. The problem on page 228 states methane gas, which is CH4, and it tells us what methane is, so you didn't need to have that memorized. Added to oxygen gas will yield, there's our yield arrow, and this, if you're wondering what this triangle is, this delta symbol, it just means a chemical change. Something is causing these two reactants on the left side of the arrow to produce two different products on the right side of the arrow. So two reactants, two products. Methane gas plus oxygen gas, notice we have our symbols, all of these chemicals are gases, will produce carbon dioxide gas and water. But our job is to figure out if the equation is balanced or not. What you need to do, and I tell my students, this is kind of like solving a puzzle. Some students, believe it or not, they enjoy this. Your job is to first make sure you've written the chemicals correctly, and then we have to see if the total number of atoms of each element is the same on both sides, because you cannot create atoms and you cannot destroy atoms in a regular chemical process. So first off, I think we should identify the elements that are involved in this particular chemical reaction. There are three. If you're wondering what this table is that I've created, it says element, and we're going to list the elements. R is going to stand for how many of them there are on the reactant side. This entire left side is reactant side. And the P, of course, is going to stand for the product side. And it doesn't matter which order we list the elements, but let's just go from left to right. And every time we see a new element, we'll write it down. The first element that I see is carbon. So we're going to write down, make sure my board doesn't fall. We're going to write down, carbon. Before we look at numbers, let's look at the next element. The next one that I see is hydrogen. So we will put hydrogen down below carbon. The only other element involved as I scan this entire chemical formula is oxygen. It's actually in a lot of spots, and I'll talk about that in just a few seconds, and how you don't want to start by balancing an element that's in a lot of spots. But the last element is oxygen. So we have three of them: carbon, hydrogen, oxygen. Like I just mentioned, there's no rhyme or reason to this. There are a few tips and tricks that I'll show you along the way to balancing chemical equations. But first, our objective is to put whole number coefficients in front of the chemicals that need them. Not every chemical needs a coefficient. Keep in mind, I said it's a whole number because we need to balance out the total number of atoms. We know that the chemicals are already written correctly, so we're not going to be doing subscripts at all. This has nothing to do with adding subscripts. You can't change oxygen and make it O3 on this side, because O3 is actually ozone, and it's not oxygen gas that we're breathing in and that's abundant in our atmosphere. So we're doing whole number coefficients. The first tip I can show you while we're on this first problem is, like I said, avoid an element that is in a lot of spots in the equation. Notice there are 1, 2, 3, 4 chemicals here, 2 reactants, 2 products. Oxygen is in 3 of the different chemicals. Let's maybe start with a different element like carbon or hydrogen and see if we need to make any changes. And if we do need to make changes, that will change our total number of oxygens. Let's start with carbon. Carbon, our reactant. How many carbons total do you see in both of those chemicals on the reactant side? I only see one because there's no subscript. 1 carbon on the reactant side. Go to the product side. Between these two chemicals, how many total carbons do you see? There are 1. So as of right now, the number of carbons on both sides of this equation, it's balanced. We're good to go for right now. We might have to make changes. We'll see. Next, let's do hydrogen. I'm scanning the entire left side here, the reactant side, and I see a total of 4 hydrogens. Notice there's no hydrogens in this compound, this chemical, this molecule, this O2 molecule, but there's 4 hydrogens here total. So let's put 4 on the reactant side for hydrogen. Please go to the left-hand side, and we're scanning, and we're looking for H's, and we see a total of 2 of them. So this is where you're going to need a whole number coefficient. We're not going to remove any of this because you can't remove any hydrogens from a methane molecule. We need to show that we need more water. We need a total of 4 hydrogens on the right side because as of right now, there are only 2. So this is going to end up changing, and I'm going to do this by adding a whole number coefficient in front of water. It's a big whole number in front of the element symbol. And you need to ask yourself, well, wait, how do I get 4 total hydrogen atoms? Instead of me writing water twice like that, and I'm going to grab my paper towel here so I can erase this. Instead of writing water twice and taking up time, what we do is we put a 2 in front of the entire molecule. That tells us that we have 2 molecules now, 2 waters. So if you think about the distributive property that you most likely learned in a math class, probably algebra, you can distribute this whole number coefficient to the entire chemical, both elements, hydrogen and oxygen. So what I'm trying to say is when we do this, we now make it, because we have 2 waters, 2 times 2, 4 hydrogens and 2 oxygens. But I'm not worried about oxygens right now. I'm looking at the fact that I now have, based on this whole number coefficient, 4 hydrogens. Now we don't have a choice. Now we have to look at oxygen. But I suggest, here's another trick with this type of reaction. You'll see more of these types. Start on the side that you made changes on. We haven't made any changes over here. And the cool thing is we have oxygen, even though it's O2, we have oxygen all by itself on this side. So let's count up our oxygens on the product side. We'll write it down and we'll see what we need to do, if anything, on the reactant side. Here we go. 2 oxygens total on the reactant side. It's really hard to write this left-handed. 2 oxygens on the reactant side, and if we're counting, don't forget there's oxygens in both of these chemicals here. 2 oxygens because of the subscript 2, plus, right here, check out the distributive property. 2 times 1. There are 2 oxygens here in the CO2, and there's a total of 2 oxygens in the water. If you add those up, because that's everything on this side, there are 4. Well, everything's good except this right here. This doesn't match. We need to put something. We need to put a whole number coefficient in front of the O2. I did not give myself enough room to do this. What number could go in front of an O2 molecule to make it a total of 4 and match the product? If you think about the distributive property, you simply need 2 oxygen gas molecules, 2 O2s. No subscript changes, just whole number coefficients. 2 times 2 is 4. This is now a balanced equation. If you remember what I've been talking about when we were in school, I would always ask you about a about a ratio. And you guys got really good at talking about a ratio. If you look at this now balanced chemical reaction, for every 1 methane gas molecule, you would need 2 molecules of oxygen gas. you would get, on the product side, 1 molecule of O2 and 2 molecules of water. It's a 1 to 2 to 1 to 2 ratio. Now that we've talked and learned about moles, you can extend that quantity beyond just a single molecule. What I want to say now is for every 1 mole of methane, you would need, or 2 moles of oxygen would be required, 2 moles of oxygen gas. 1 mole to 2 moles, and you would get, as products, 1 mole of carbon dioxide gas to every 2 moles of water. I'm going to pause and throw on another equation that we're going to balance, a different example. Okay, last reaction for this particular video of this particular section. This is a sample problem 8.4 on page 231. It discusses an unbalanced chemical equation that includes polyatomic ions. Another trick that you can use, if it's available to you, is that you can keep polyatomic ions like this phosphate here. If you see the same polyatomic ion in the same form on the other side of the equation, you can balance them as an entire group. You can keep them as a group. Let me explain a little bit further what I'm trying to say. First, let's look at the elements involved. Or let me explain the equation first. This is a chemical called sodium phosphate. It's aqueous, which means both of these chemicals are dissolved in water. Water's helping the reaction to completion. Sodium phosphate plus aqueous magnesium chloride, written as MgCl2, will yield magnesium phosphate, which I forgot to put a state of matter. That is going to be a solid. That is going to come out of solution. That's going to be what we call a precipitate. And a byproduct of that is going to be NaCl, also aqueous. Keep in mind, assume that all of these chemicals are written correctly, no subscripts. We're going to identify the elements involved, and we're going to make sure that the numbers of atoms are the same on both sides, and we'll make sure we do that by adding coefficients if we need to. First element I see is sodium. We'll write down sodium. The book uses Na plus because this is an ionic compound. So if you were to break it apart, it would be a sodium atom that has lost 1 electron. I'm not going to worry about that. Let's just count our elements, okay? And here's the thing. The book has, instead of just counting phosphorus and oxygen separately, you see that there's PO4. I want you to be able to recognize that is called the phosphate ion. It's on your periodic table of ions. It's by itself, it's a PO4 with a 3 minus charge. But what the book is trying to tell you in this problem is that you can keep phosphate as an entire group. So I'm going to put PO4. What else do we have here? We have 2 other elements that are involved. We have magnesium, Mg, and we have chlorine, Cl. Let's see what we can do here and see what we need. Sodium, let's start there. I see a total of 3 on the reactant side. I see a total of, I'll write this so you can see it. And I don't do this anymore, but I have lots of experience balancing chemical equations. If you feel comfortable with this, that's fine. You don't have to do this table. You can just go up and look element by element and see how you can solve the puzzle. It will work out eventually with whole number coefficients being in the right spots and the number of atoms of each element being the same on both sides. Sodium, 3 on the left, 1 on the right. The most logical thing to do here would be to put a 3. But stay with me. You're going to see a change here. I recommend solving these problems in pencil. The most logical thing to do here would be to put a 3. 3 times 1 Cl, I'm sorry, not Cl, 3 times 1 Na will match that Na. So right now, Na is good to go. Let's look at our phosphate. We can keep this as an entire group because it looks the same on both sides. There just happen to be 2 phosphates on the right. So the most logical thing to do here is to look and say, wait a minute, I need 2 phosphates on the left. I can't add parentheses and a subscript. We're not doing subscripts. I need more units of this. I need 2 of these because I need 2 phosphates on the left to match the 2 on the right. So what I'm going to do is, I don't know how I'm going to do this, but I'm going to put a 2 in front of that entire chemical. So now we have 2 phosphates. We had originally 2 phosphates on the product side, and now we have 2 phosphates on the reactant side. But we did something just now. When we balanced out our phosphates, we did something to the sodiums. If you look now, there's 3 sodiums still on the product side, but how many sodiums do we have on the reactant side? Think about distributive property, not addition, it's multiplication. There are now a total of 6 sodiums. So it was basically the phosphate that sort of drove this number and made us have to put this number. So now we have to go back. That's why I said do this in pencil. And I have the ability to do this in dry erase. This 3 is not going to work because these are the only 2 spots with Na. If I have 6 NAs here, which I have to change this. I have 6 on the reactant side, right? I need a coefficient in front of here. No subscripts, so we're thinking 1. What times 1 would equal a total of 6? And we would actually put, believe it or not, a 6 coefficient in front. So now we have 6 sodiums on the reactant side, 6 on the product side. Let's now look at the next element, magnesium. Let's look at the reactant side. I see 1 magnesium. On the product side, the only spot I see magnesium is there. I see a subscript of 3, no coefficient in front of it. So that does not match. They are not balanced. Something's got to go in front of there, a whole number coefficient. The most logical number to put would be a 3. And that balances out my magnesiums. 3 times 1 is 3. But what else does it do to the chlorines? Believe it or not, it helps us to solve our puzzle. Let's look at our last element now, chlorine. 3 times 2 is 6 on the reactant side. And look, because we put that 6 coefficient on the product side when we were balancing out our sodiums, we have 6 times 1, 6 chlorines on the right. Ladies and gentlemen, that is the balanced equation using polyatomic ions. The ratio of these 4 chemicals, whether you're talking molecules or moles, is a 2 to 3 to 1 to 6. You don't need to put 1s as coefficients. For every 2 of these, you need 3 of these. You get 1 of these, and you get 6 of those, and every element is balanced.